Jetzt machen wir weiter mit Professor Dr. William Happer. Professor Dr. William Happer ist unter anderem Spezialist für moderne Optik und Strahlungsausbreitung in der Atmosphäre. Er ist emeritierter Professor im Fachbereich Physik der Princeton University, an der er auch Physik promovierte. Er lehrte nachträglich auch in Physik an mehreren amerikanischen Universitäten. 1991 wurde er von Präsidenten George Bush zum Direktor für Energieforschung im Energieministerium ernannt. 1991, ab 2018 diente er ein Jahr lang als Berater des Präsidenten und als leitender Direktor neuer Technologien im Nationalen Sicherheitsrat des Weißen Hauses. Er ist Mitbegründer der CO2 Coalition, eine gemeinnützige Organisation in den USA, die die Vorteile des atmosphärischen Kohlendioxids für das Leben bekannt macht. In der wissenschaftlichen Welt ist er vor allem für den Natriumlaser-Leitstern bekannt, der von Astronomen auf der ganzen Welt tatsächlich benutzt wird, jede Nacht, um die Verzerrung von Teleskopbildern durch die atmosphärischen Turbulenzen zu korrigieren. Happer meint selber, dieser Natriumlaserleitstern funktioniert jedes Mal. Die Klimamodelle für die Atmosphäre funktionieren hingegen nur selten. Ich heiße Sie herzlich willkommen auf unserer Bühne, Mr. Professor Dr. William Happer. Welcome on stage. Thank you for your presentation today.
Well, first, I'm very grateful to the organizers of this conference for inviting me. I've never been to Vienna. It was a thrill. Tom Nelson and I visited Wolken's grave day before yesterday, and it was just so exciting to be here. And anyway, many thanks for inviting me. And I'm going to talk about the nuts and bolts of how radiation goes through clouds, and we will hear more about clouds. We heard from John Clauser yesterday, and we'll hear from Hendrik Svensmark and Nir Shaviv about the connection between clouds and cosmic rays, I hope, pretty soon. So let me just get started with the first transparency. People have been, could I get the next, oh, here. All right, so actually people have been looking at clouds for a very long time in a quantitative way. This is one of the first quantitative studies. It was done about 1800, and this is John Leslie, who was a Scottish physicist, and he built this gadget here. He called it an ethereoscope. But basically what it was designed to do was to figure out how effective the sky was in causing frost. You know, if you live in Scotland, you know, worry about frost. And so it consisted of two glass bulbs, and they had a very thin capillary attachment between them, and there was a little column of alcohol here. The bulbs were full of air, and so if one bulb got a little bit warmer, it would force the alcohol up through the capillary, and if this one got colder, it would suck the alcohol up. And so he set this device out under the clear sky, and it was very much like the device that is shown on the wall out here by Martin Steiner and his colleagues. So you might want to go look at that. It's a very similar operation to this. And here's what he described that he saw. The sensibility of the instrument is very striking, for the liquor incessantly falls and rises in the stem with every passing cloud. In fine weather, the ethereoscope will seldom indicate a frigorific impression of less than 30 or more than 80 millesimal degrees. He's talking about how high this column of alcohol would go up and down. If the sky became overclouded, it may be reduced to as low as 15. This is how much the sky cools, or even 5 degrees. When the congregated vapors hover over the hilly tracts, we don't speak English that way anymore, but I love it. So, so the point was, even in 1800, Leslie and his colleagues knew very well that clouds have an enormous effect on the cooling of the Earth. And you know, anyone who has a garden knows that, you know, if you have a clear, calm night, you're likely to get frost and lose your crops. And so this was a quantitative study of that. Now, it's important to remember that our atmosphere, if you go out today, the atmosphere is full of two types of radiation. There's sunlight, which you can see, and then there is the thermal radiation that's generated by greenhouse gases, by clouds, by the surface of the Earth, which you can't see, but you can feel it if it's intense enough by its warming effect. And these curves practically don't overlap. So we're dealing with two completely different types of radiation. There's sunlight, which scatters very nicely and off of not only clouds, but molecules. It's the blue sky, the Rayleigh scattering. And then there's the thermal radiation, which actually doesn't scatter at all on molecules. So greenhouses are very good at absorbing thermal radiation, but they don't scatter it. Clouds scatter thermal radiation. And what's plotted here is the probability that you will find a photon of sunlight between, you know, log of its wavelength and the log of, in this interval of the wavelength scale, the log wavelength scale. So that's about all we need to say about this at this point. Now, since Leslie's day, two types of instruments have been developed to do what he did more precisely, and one of them is called a pyranometer, and this is designed to measure sunlight coming down onto the Earth on a day like this. So you would put this instrument out there and it would read the flux of sunlight coming down. It's designed to see sunlight coming in every direction, so it doesn't matter whether the sun is shining this way or vertically up. It's calibrated to see them all. So let me show you a measurement of a calorimeter, a pyranometer. So this is actually a curve from a sales brochure of a company that will sell you one of these devices, and it's comparing two types of detectors. You can see they're very good. You can hardly tell the difference. I can't see them. Maybe there's a little difference here. But that's not the point. The point is that if you look on a clear day with no clouds, you see sunlight beginning to increase at dawn. It peaks at noon and it goes down to zero. And there's no sunlight at night. So we've got half of the day over most of the Earth where there's no sunlight in the atmosphere. Here's a day with clouds. It's just a few days later. This is day of the year going across this way. And you can see every time a cloud goes by, the intensity hitting the ground goes down. You get a little clear sky, it goes up, down, up, down, up, down. And on average, at this particular day, you get a lot less sunlight than you did on the clear day. Well, you know, nature is Einstein had this wonderful quote, you know, that, God is subtle, but he's not malicious. And so what he meant that nature does all sorts of things you don't expect. And so let me show you what happens on a partly cloudy day here. So this is data taken near Munich, München. And the blue curve is the measurement. The red curve is the intensity on the ground if there were no clouds. This is a partly cloudy day. And you can see that there are brief periods when the sunlight is much brighter on the detector on a cloudy day than it is on the clear day. And that's because coming through clouds, you get focusing from the edges of the cloud pointing down toward where your detector is. That means that somewhere else there's less radiation reaching the ground. But this is rather surprising to most people when they first learn about it. I was very surprised to learn about it. But it just shows that the actual details of climate are a lot more subtle than you might think when you first start thinking about it in your office. Okay, now that visible light, that only happens during the daytime. We saw that the light stops at night. Then there's a second type of important radiation, which is the thermal radiation. And that's measured by a similar device. It's, again, very similar to the equipment that Martin Steiner's group has. What you have is a silicon window that passes infrared, which is below the band gap of silicon, so it passes through it as though it were transparent. And then there's some interference filters here to give you further discrimination against sunlight. So actually sunlight practically doesn't go through this at all. So they talk about it as being solar blind. It doesn't see the sun, but it sees thermal radiation very clearly. And but there's a big difference between this device and the sunlight sensing device I showed you, because this is most of the time actually radiating up, not down. So if you put this out in the open air, this detector normally gets colder than the body of the instrument. And so it's carefully calibrated so that you can compare the balance of downcoming radiation with the upcoming radiation. Upcoming is normally greater than downcoming, and get a measurement of the downwelling flux. So I'll show you some measurements here. So here are some measurements actually in Greenland, in Thule. And these are watts per square meter on the vertical axis here. And the first thing to notice is that the radiation continues day and night. If you look at the output of the pyrgeometer, you can't tell whether it's day or night, because the atmosphere is just as bright at night as it is during the day. And the big difference, however, is clouds. On a cloudy day, you get a lot more downwelling radiation than you do on a clear day. So here's nearly a full day of clear weather. Here's another several days of clear weather. And then suddenly it gets cloudy. And the reason for this is the bottoms of the clouds are relatively warm, at least compared to the clear sky. And I think if you put the numbers in, this cloud bottom is around 5 degrees centigrade, so it was fairly low cloud. It was summertime in Greenland. And this corresponds to about minus 15 degrees for the clear sky. Okay. So there's a lot of data out there, and there really is downwelling radiation. There's no question about that. You measure it routinely. And finally, I've been talking about looking up at what's coming down, and now you can do the same thing looking down from satellites. So this is a picture that I downloaded a few weeks ago to get ready for this talk from Princeton, and it was evening. It was, I don't know, 5 o'clock, I guess, at Princeton, 6 o'clock at Princeton, so it was already dark in Europe. So this is a picture of the Earth from a geosynchronous satellite that's parked over Ecuador. You're looking down on the on our hemisphere, the Western Hemisphere, and this is a filtered image of the Earth in blue light at 0.47 micrometers. So it's a nice blue color, not so different from the sky. And it's dark where the sun is set, so absolutely no sunlight coming up here. The Earth doesn't spontaneously emit sunlight, and still a fair amount of sunlight over the United States and the further west. But here is exactly the same time, and from the same satellite, the infrared radiation coming up at 10 microns, I believe, 10.3 microns. This is right in the middle of the infrared window, where there's not much greenhouse absorption. There's a little bit from water vapor, but very little, trivial from CO2. And here you can see, you can't tell which side is night and which side is day. So even though the sun has set over here, it is still glowing nice and bright. There's a sort of a pesky difference here, because what you're looking at here is reflected sunlight over the intertropical convergence zone. So there are lots of high clouds that have been pushed up by the convection in the tropics. And so this means more visible light. Here you're looking at emission of the cloud top. So this is less thermal light. So white here means less light. White here means more light. So it's you have to calibrate your thinking to that. But just to come back to John Clauser's talk, the striking thing about all of this, if you look at the Earth, it's covered with clouds. You know, you have to look hard to find a clear spot of the Earth. Roughly half of the Earth maybe is clear at any given time, but most of it's covered with clouds. So if anything governs the climate, it is clouds, and so that's one of the reasons I admire the work that Svensmark and Shaviv have done so much, because they're focusing on the most important mechanism of the Earth. It's not greenhouse gases, it's clouds. You can see that here. Okay, so this is a single frequencies. This is a single frequency. Let me show you what happens if you look down from a satellite and look at the spectrum. So this is the spectrum of light coming up over the Sahara Desert. This is measured from a satellite. And so here is the infrared window. There's the 10.3 microns I mentioned in the previous slide. It's a clear region. So radiation in this region can get up from the surface of the Sahara right up to outer space. And notice that the units on these scales are very different. Over the Sahara, the top unit is 200, 150 over the Mediterranean, and it's only 60 over the South Pole. But at least the Mediterranean and the Sahara are roughly similar. So the right side here, these three curves on the right are observations from satellites. And the three curves on the left are calculations, modeling that we've done. And the point here is that you can hardly tell the difference between a model calculation and an observed satellite image. So it's really straightforward to calculate radiation transfer. So if someone quotes you a number in watts per square centimeter, you should take it seriously. That's probably a good number. If they tell you a temperature, you don't know what to make about it, because there's a big step between going from watts per square centimeter to a temperature change. So all the mischief in the whole climate business is going from watts per square centimeters to centigrade or Kelvin. Let me point out some other interesting things here. Many of you probably are not used to looking at this, but this is CO2 here, and what that little spike in the center is the upper stratosphere where it's hot. So there's where all the ozone is being absorbed, so the temperature at the maximum in the stratosphere is not very different from here on the ground. On the edges here is the lower stratosphere, the upper troposphere, where the temperature is really cold. It's minus 50 centigrade, 220 Kelvin or something like that. So looking at this immediately, you can tell that the stratosphere heats as you go up. It's not constant temperature. Mediterranean is very similar, but look at Antarctica. In Antarctica, the greenhouse gases actually do the opposite. Here you see greenhouse gases are suppressing the amount of radiation that would go to space compared to the optimum, the maximum possible. This is the Planck curve for the surface. But over Antarctica, the greenhouse gases actually increase the amount of radiation going to space. So they're anti-warming over Antarctica. And this is a wintertime temperature where there's a huge temperature inversion over Antarctica. The ice is really cold, and the air above it is quite a bit warmer. So a lot of interesting stuff going on here. But this is all cloud-free, let me say. But I will say, if you look at imaging from cloud tops, they look like Antarctica. So if you want to know what a satellite sees looking down on a cloud, think of Antarctica. It usually looks like that because the cloud top is very similar to the ice sheet on Antarctica. Okay, so let me say just a few words about clear sky. because that is the simplest. It's not the topic of the talk. The talk is supposedly on clouds, but this is a calculation with the same codes that I showed you in the previous slide, which, as you can see, work very well. And it's worth spending a little time on this. This is the famous Planck curve. That was the birth of quantum mechanics, and there's Max Planck, who figured out what the formula for that curve is and why it was that way. And this is what the Earth would radiate at 15 degrees centigrade if there were no greenhouse gases. So you would get this beautiful smooth curve, the Planck curve. If you actually look at the Earth, as I showed you from the satellites, you get a raggedy, jaggedy black curve. And so we like to call that the Schwarzschild curve, because the person who showed how to do that calculation was Karl Schwarzschild, who tragically died during World War I. Big loss to science. And there are two colored curves that I want to draw your attention to. They're important. The green curve is what Earth would radiate to space if you took away all the CO2. So if you, it only differs from the black curve, you know, in the CO2 band here. This is the bending band of CO2. It's the main greenhouse effect of CO2. There's a little additional effect here. This is the asymmetric stretch, but it doesn't contribute very much. And then here is a red curve, and that's what happened if you double CO2. So notice the huge asymmetry. If taking all 400 parts per million of CO2 away from the atmosphere causes this enormous change, 30 watts per square centimeter. It's the difference between this green 307 and the black 277. That's 30 watts per square meter. But if you double CO2, you practically don't make any change. So this is the famous saturation of CO2. You know, at the levels we have now, adding even a lot, 100% increase of CO2, only changes the radiation to space by 3 watts per square centimeter, the difference between 274 for the red curve and 277 for the curve for today. So it's a tiny amount, it's 1%. 1% for doubling. So 100% increase in CO2, 1% decrease of radiation to space. And you know, that allows you to estimate the feedback-free climate sensitivity in your head. And so I'll talk you through the climate-free sensitivity. So doubling CO2 is a 1% decrease of radiation to space. If that happens, then that means the Earth will start to warm up. But it will radiate as the fourth power of the temperature. So temperature starts to rise. But if you've got a fourth power of the temperature only has to rise by 0.25% absolute temperature. So 1% for forcing watts per square centimeter is 0.25% of temperature in Kelvin. And so the ambient Kelvin temperature is 300 Kelvin, say, a little less. 0.25% of that is 0.75 Kelvin. So the feedback-free equilibrium climate sensitivity is less than 1 degree. It's 0.75 centigrade. It's a number you can do in your head. You don't need to you don't even need a pencil and paper. So so when you hear about 3 centigrade instead of 0.75 centigrade, that's a factor of 4. All of that is positive feedback. So is there really that much positive feedback? And if there is, that's kind of funny in itself, because, you know, most feedbacks in nature are negative. You know, there's this famous Le Chatelier's principle, which says that, you know, if you perturb a system, it reacts in a way to dampen the perturbation, not increase it. There are a few positive feedback systems that we're familiar with. For example, high explosives have positive feedback. So if the Earth's climate were like other positive feedback systems, all of them are high explosives. And so it would have exploded a long time ago, you know. So that's the way explosives are. You know, sooner or later you have an accident and it explodes. But the climate has never done that. So the empirical observational evidence from geology is that the climate is like any other feedback system. It's probably negative. Okay, so I'll leave that thought with you. And I'll say this, stress again, this is clear skies, no clouds. If you add clouds, all this does is suppress the effects of the greenhouse gas, changes of the greenhouse gas. Let me just check how my time is doing. Okay, not too bad. All right, but let me, let's see, before I go back. I'm now going to abuse your patience by talking a little bit about equations. So I must apologize to you here who don't live and breathe differential equations. I do, so and to me they're beautiful. You know, when I see a nice equation, it's like a sonnet or something. That's why I like Boltzmann's grave so much. It had an equation on it, and so it was worth it just to go see his equation. But the transfer of radiation, if you have no clouds, is given by the Schwarzschild equation. So this is the Schwarzschild equation. That's Karl Schwarzschild's equation here. So it's worth pausing and talking about it a little. Don't be intimidated. So there are two factors here in brackets. One is the Planck intensity, and so that's this blue curve here that Planck invented. So that has nothing to do with greenhouse gases. It only depends on temperature and on frequency. So this is at a particular frequency along this axis. And the other is the intensity, the thing you're interested in, which is carrying radiation to space. And this says that if you go up in altitude, Z is the altitude, that this will change if there's a difference between these two. So what radiation in space is trying to do all the time, it's trying to make the intensity equal to the Planck intensity. So it's trying to make the right side of this equation 0. And we saw a nice, again, Martin Steiner's group showed a nice demonstration of that this really is 0 in their apparatus. They showed if you greatly increase the amount of CO2 in the tube that they had, you change the coefficient in front of this, but these two terms remain the same. So it was 0 before. If you make this 10 times bigger, it's still 0, because, you know, anything times 0 is 0. So that's the simple case with no clouds. So now let's talk about clouds, the theory of clouds. And we've already seen clouds are very important. And here is the formidable equation of transfer. This has been around since Schwarzschild's day. Schwarzschild left out this miserable integral here. Actually, I like the integral, but it makes it a lot harder to work with. And we'll say a few words about this. And so this, some of the symbols here, there's the intensity, I, intensity. This represents scattering, so that unlike thermal radiation, if you have a cloud, thermal radiation on a greenhouse gas where it comes in and immediately is absorbed, there's no scattering at all. If you hit a cloud particle, it will scatter this way or that way, or some maybe even backwards. And so all of that's described by this integral. So you've got incoming light at one direction, and you've got outgoing light at a second direction. So you have this integral differential equation, which is hard to solve. And then at the same time, you've got thermal radiation. So the warm particles of the cloud are emitting radiation, creating photons which are coming out and increasing the Earth glow. And this is parameterized by two parameters. This is called the single scattering albedo. John Clauser talked about the albedo of the Earth yesterday, but even a single cloud particle has an albedo. So what this is the fraction of radiation that hits the cloud that is scattered as opposed to absorbed and being converted to heat. Okay, it's a very important parameter, and for visible light and white clouds, typically 99% of the encounters are scattered. So this is close to 1. It's 0.99 typically for white clouds. But for thermal radiation, it's much less. So water doesn't scatter as efficiently for thermal radiation. So it's about a half for typical thermal radiation. And then there's the scattering amplitude in physics. I know there's some physicists here. We would call this the differential scattering cross-section. But in this community, radiation transport is called a phase function. You know, phase is used for so many things in science. It's very confusing. But anyway, we're stuck with that nomenclature. Okay, so it's a complicated equation. If anyone is really seriously interested, you can read a lot more about it here. I'm just going to try and give you the flavor of it in the remaining time I have, and I'll try and make this short because I know we're all eager to have lunch. And so a few words about what's in that. There's the location of where you measure the intensity. There's the direction of the intensity. So those are the independent variables. And then the big problem is that in spite of all the billions of dollars that we have spent, these things which should be known and would have been known if there hadn't been this crazed fixation on carbon dioxide and greenhouse gases, and so we've neglected working on these areas that are really important as opposed to the trivial effects of greenhouse gases. Attenuation, so attenuation in a cloud is both scattering and absorption. There's the fraction that's scattered as opposed to being absorbed. There's the Planck intensity that at least is usually well known if you know the temperature in the cloud. And then the phase function. And the one unknown is the intensity of the light. Okay. Of course, these equations, you have to solve them for every different frequency of the light because, especially for molecules, there's a strong frequency dependent. It's a lot less for clouds. Okay, so the trick in solving this is to simplify the equation with what we call the two-in-stream radiation transfer theory. This is something that at the time we worked on this, we didn't realize it was already known to the neutron scattering community. And I'll say a little bit about the history of that in a minute, but we stumbled on it independently, not the first. But first thing you do is that if you looked at the clouds in the satellite photos, many of them are layered clouds. Of course, there are scattered clouds over much of the Earth as well, but at least one could start by looking at a planar situation where you have one cloud layer, a second cloud layer, a third cloud layer, infinitely spread out. And so instead of three-dimensional locations, you only have the altitude, and instead of every possible direction in space, you have a cone of directions, you know, so you only need Legendre polynomials, you don't need spherical harmonics. Okay, so the second trick is instead of doing the integral for scattering, you sample the directions. So it's a little bit like quantization of spins, and you know, for a quantized spin, it can point this way, this way, this way. There's a finite number of directions you can point. And so for radiation, you can do the same thing. This is again, it wasn't, it seemed like new when we first stumbled on it, but it turns out it was known before. And the sampling is interesting. You sample it at the zeros of the 2n Legendre polynomial. So it's a funny way of sampling. Some of you may know a little bit about communications theory, and there's a lot of sampling done here. So this is quite analogous to Shannon-Nyquist's sampling of a communication signal. But for communications, you do uniform sampling. Every Nyquist period, you sample the voltage or current. And here, you sample it at these non-uniformly spaced directions of radiation. And finally, you have to be careful to distinguish radiation that's generated thermally in the cloud, that's created by the particles just converting heat into radiation, to external radiation that's scattering and going the other way, either getting out of the cloud or being converted to heat and disappearing. And it turns out that this satisfies it has very similar properties to Kirchhoff's laws for radiation transfer in simpler systems. So there's a scattering matrix, there's an emissivity matrix, and they add to one. So I'll quickly show you that. So first of all, let's talk about the difference. There are two types of intensity in our atmosphere. So looking out today, what we see is the scattered intensity from sunlight. And there you typically see the blue sky. This is scattering from nitrogen and oxygen, and so that preferentially scatters shortwave light. It goes as the inverse fourth power of the wavelength. So the sky's very blue. And then there's the scattering from little droplets of water or ice crystals, and that scatters every color almost equally. And so the clouds look the same color as the sun, but the clear sky scattering is much bluer than the sun is. Yeah. And then there's thermal emission. Well, the atmosphere doesn't normally thermally emit visible light. To get thermal emission of visible lights, you can look at fireworks. That's thermal emission of light, but that's not a normal condition of the atmosphere. Or you can see a lightning flash, and that's thermal emission, but it's not the normal state of the atmosphere. So a big difference between these two types of radiation is this emission is mostly characteristic of thermal radiation, not the sunlight, and scattering occurs for both of them in clouds. So I mentioned that these tricks for treating clouds go back to the neutron scattering folks, and this is Giancarlo Wick. I knew Giancarlo. He was still alive and a professor at Columbia when I was a young man, and he talked just like Nicola. He had a strong Italian accent, and he was a very smart guy. Giancarlo, after he completed his PhD, he went to Leipzig and he befriended Heisenberg. So he was a close friend of Heisenberg, worked there in 1930 or 31. And then in 1932, Fermi called him back to Rome, and so he was Fermi's right-hand man in Rome in the 30s when all of these wonderful neutron experiments were done in Rome, which eventually won Fermi his Nobel Prize. And then when Fermi was awarded the prize, he was able to leave Italy, which was under control of Mussolini at the time. You couldn't get out easily, but Giancarlo could not because he didn't have a Nobel Prize, so he was stuck in Italy throughout the war. And while he was there, he managed to write this wonderful paper which showed how to sample the directions of neutrons in the way that I just mentioned, using the zeros of Legendre polynomials. It turns out that makes most of the integrals exact, under some conditions. And so the key is that you replace an integral over all space by an axially symmetric integral, and then a sampled integral. This is a Gaussian quadrature. So somehow Giancarlo knew about Gauss's work 100 years earlier. He was an amazing guy. He's best known for particle in field theory. So there's something called Wick's theory. If any of you have the background, you will know about it. So a lot fewer people know about his work on radiation and neutrons in about his field theory work. But amazingly, what he did was almost identical to Claude Shannon's work for communications. So both of them were using sampling to convert from an integral to a discrete number of samples. And of course, that's wonderful today because you solve that with computer programs today. And it's a very efficient way to do things. Okay, so here's a few examples. I mentioned that you have to take into account different directions of scattering. One thing you quickly notice with cloud particulates is you have strong forward scattering. It's not isotropic at all. And so whatever theory you put together has to be able to handle arbitrary directions of scattering. And so this is a typical scattering, a strongly forward scattering phase. So if you come in with red rays like this, then you will scatter mostly in the forward direction the same way you came in, but some a little bit to the right, even further to the right, etc. You can think of these as sort of cones. Or if you come in horizontally, you tend to scatter horizontally on the way out. So that is a feature. Here's a simple example of a calculation for a toy cloud. It's a cloud with a bottom here on this green line, a top here on this green line. This is optical depth going up and down this way. And so below the cloud is a Planck radiator that's putting out these red rays here. And they've got a Lambertian angular distribution. And so that's the rays coming in. Some of them are reflected back, and a very small fraction of the incoming rays from the bottom get through to the top. But at the same time, this is a warm cloud, so the cloud is radiating itself just from thermal radiation, and that's the blue rays. So I mentioned again, you have to always remember there's two types of radiation. There's the thermally generated radiation, the blue here, and the external radiation, which in this case is red rays, and they're simultaneously there. And I'm sure worn out my quota of sympathy for equations, so this is the very last the very last equation I'm going to show you. But that previous slide, it turns out that, of course, you're usually not interested in the radiation inside the cloud. So it's very much like, physics, where when you look at scattering, you're interested in which way the proton goes after it leaves the target, or compared to how it came in. And so you have a scattering matrix. And here again, clouds have scattering matrices, just as particles do. And so, for example, if you come in with Planck radiation on the bottom of a cloud, then the cloud scatters much of the radiation downward. These red rays represent rays coming from the bottom of the cloud, and the red rays on the top are those photons that have managed to random walk through the cloud and get to the top and get out. And so it turns out that the output radiation is proportional to the input, and the constant of proportionality is the scattering matrix. So there's a scattering matrix that relates a cause, the input radiation, in this case simple coming up from the bottom, to the output radiation. And this is thermal radiation. It was very similar, but in this case, the cause, since there's no external radiation, it's just the Planck thermally generated radiation inside, which is also isotropic. It's equal in all directions. But by the time it gets out of the cloud, it's very strongly limb darkened. So if you look at the radiation coming from clouds, actually, it's true that you get a lot more thermal radiation coming up than from horizontal direction. So in that sense, it's a lot like the sun, but for different reasons. The sun is strongly limb darkened because it gets hotter as you go to the inside. But even if the cloud's isothermal, it's limb darkened. And these two key matrices add up to one. And that was something that was first noticed by Gustav Kirchhoff, Kirchhoff and Bunsen, the same Kirchhoff. So let me, we're getting close to lunchtime, so I'm going to finish up and with a few summary words. This, by the way, was taken by Harrison Schmidt, who was a friend of mine, and on one of the first moonshots, the one he was on. And it was taken in December. And looking at this, you can see that they were south of Madagascar when the photograph was taken. You can see it was winter because here's the intertropical convergence zone. It's quite a bit south of the equator. It's moved way south of India and Saudi Arabia. And by good luck, they had the sun behind them, so they had the whole Earth irradiated. So there's a lot of information there. And again, let me draw your attention that how much of the Earth is covered with clouds. So very, very small parts of the Earth can actually be directly affected by greenhouse gases of the order of half. So the takeaway message is that clouds and water vapor, they're much more important than greenhouse gases for Earth's climate. The second one is that the reason they're much more important is doubling CO2, as I indicated in the middle of the talk, it only causes 1% difference of radiation to space. It's very tiny effects because of saturation. There's no question it's saturated. People like to say, well, no, but you really can't argue that one. Even the IPCC gets the same numbers that we do. They know it's true. And but covering half of the sky with clouds will decrease solar heating by 50%. So for clouds, it's 1 to 1. For greenhouse gases, it's 100 to 1. So if you really want to affect the climate, you want to do something to the clouds. You have a very hard time making any difference with net zero with CO2 if you take realistic warmings into effect. And finally, abusing your patience, I did mention toward the end that there are nice theories that have been developed. I like to think about this as, during the medieval times or a little later, astronomers made their living by, or chemists made their living by promising to turn lead into gold, right? And so one would hope that with all the money that we've spent trying to turn CO2 into a demon, that some good science has come out of it. And from my point of view, this is a small part of it, this two-inch scattering theory, that I think will be here a long time after the craze of over greenhouse gases has gone away. And I hope there will be other things too. I think other things you can point to are the better instrumentation that we've got, satellite instrumentation, ground instrumentation. So that's been a good investment of money. But the money we've spent on supercomputers and modeling has been completely wasted, in my view. So, okay, thank you very much.